Good morning all. Today in this video we are going to discuss about the regulated power supply. So what is the need of this regulated power supply? So an ordinary or unregulated DC power supply contains a rectifier and a filter circuit. That means, so for regulated power supply there is a need which contains the circuits of rectifiers and filter circuits. So need for regulated power supply. That means an ordinary or unregulated DC power supply contains a rectifier and a filter circuit. So that means already we have discussed about rectifier and filter circuit in previous videos. So briefly we are going to discuss about deeply what is a rectifier. Rectifier means which convert the signal into pulsating DC. So the function of filter here is, so the pulsating DC, the output of the regulated power supply is pulsating DC. The pulsating DC will be smoothened by the filter circuit. So the combination of this rectifier and filter circuit will be within an unregulated DC power supply. So an ordinary DC power supply has the following drawbacks. The main drawbacks in unregulated or ordinary DC power supply as follows. The first one here is the DC output voltage changes directly with input AC voltage. So in unregulated DC power supply having the main drawbacks, the first one is the DC output voltage changes directly with input AC voltage. That means the output voltage does not maintain constant with any changes occurring input AC voltage. At the same time, other drawback here is the DC output voltage decreases as the load current increases. This is due to the voltage drop in transformer windings, rectifier and filter circuits. So these are the main drawbacks in unregulated power supply. That means the output of regulated power supply will be changed with respect to the input AC voltage. At the same time, so the DC output voltage of this unregulated power supply will be decreases. The DC output voltage will be decreases as the load current increases. So this is due to the voltage drop across the transformer windings or rectifier and filter circuit. So due to these filter circuit, rectifiers and transformer windings, so the output voltage will be changed. So this is the main drawbacks in unregulated power supply. So to avoid these unregulated power supply drawbacks, we go for the regulated power supply. So a DC power supply which converts AC into DC and maintains the output voltage constant irrespective of input AC supply variations or load variations is known as regulated DC power supply. So already we know that in case of unregulated DC power supply, the main drawback is the output voltage will be changed with respect to the input AC voltage, as well as so the output voltage will be decreases. Output voltage will be decreases due to the changes in the transformer windings, rectifiers and filters. So to avoid these changes at the output voltage, we will go for the regulated power supply. That means the DC power supply which converts AC into DC and maintains the output voltage constant irrespective of input AC supply variations or load variations is known as regulated DC power supply. That means regulated DC power supply will maintains the constant output irrespective of changes in the AC input voltage and load variations is known as regulated power supply. So in this regulated power supply, so mainly first we are discussed about Zener diode. So analyzing a diode operating in the reverse bias region will show that the current through it remains essentially constant until the breakdown voltage, also called as avalanche or Zener voltage, is reached. So that means here the purpose of Zener diode utilized in this regulated power supply is to maintain the constant output voltage. For that purpose we are using the Zener diode. So in which region we are going to use the Zener diode as a regulator means in reverse bias condition we are using the Zener diode as a regulator. So that means in this reverse bias condition, so the current through the Zener diode will remain essentially constant until the breakdown voltage will be reached. So this breakdown voltage is also called as avalanche or otherwise Zener breakdown voltage. That means up to it reaches the breakdown voltage, so the output of the Zener diode will maintain constant. So the main need of regulated power supply means the output does not change with respect to the variations in input voltage and load current. So that's why here we are using the Zener diode as a regulator. Used as a regulator. At this point, the current will increase very rapidly for a small voltage change. So once it reaches the breakdown voltage, so the current will increase very rapidly for a small voltage change. Here, these are the characteristics, VI characteristics of Zener diode. So the Zener diode will be used as a regulator in case of reverse bias. So now here we are going to um, learn about the characteristics of these Zener diode in reverse bias. So this x-axis will indicate the VR, that is reverse voltage. Next y-axis will be equal to IR, that is reverse current. So when we are increasing the reverse voltage, so up to the breakdown voltage which will maintain the constant current, once it reaches the breakdown voltage, so there is a sudden changes will be occurring output current, that means reverse current. So this region of operation will be used as regulator in case of Zener diode. So in this region it maintains the essentially or it maintains the constant current with respect to the voltage. So that's why Zener diode will be used as a regulator when it is connected in reverse bias. Now, so what is the symbol of this Zener diode? So this Zener diode is also having two terminals just like a PN junction diode. Those two terminals will be called as anode and cathode. So the representation of this Zener diode with respect to the PN junction is there is a small change at the anode. So in case of Zener diode we are using just like a Z symbol at the cathode. So here, so where the symbol will be occur, that will be equal to the cathode. So besides that will be called as anode. These are the two terminals will be used in, these are two terminals in a Zener diode, anode and cathode. So these are the Zener diode terminal identification. So suppose practically, so when we are there is a Zener diode, how to identify the terminals? That is either it will be anode or cathode. How to identify that? So at the cathode end there is a simple mark at the edge that will be marked with a silver color. So the right of the silver color will be equal to the cathode. So left of the silver color will be equal to anode. So these are the two identification of Zener diode terminals, anode and cathode. Next, go for the Zener diode VA characteristics. Already we are briefly discussed about the Zener diode characteristics. Once again, I will repeat. So, in case of Zener diode, in forward bias condition. Here, what is meant by forward bias means? So, the positive terminal of the diode, suppose we can assume as, so this is equal to our battery. So, positive terminal and negative terminal. So, the here is equal to the Zener diode. So the anode terminal of the diode will be connected to the positive terminal of the battery. At the same time, so the negative, that means cathode terminal of the Zener diode will be connected to the negative terminal of the battery. Then this way of connection will be known as forward bias. In case of forward bias condition, So the VA, when we draw the VA characteristics of the Zener diode, so VA characteristic means forward voltage and forward current. So when we are gradually increasing the forward voltage, the current will be also increased linearly. So the functioning of this forward bias condition of Zener diode is just like a PN junction diode. So in case of PN junction diode, forward voltage increases, the forward current is also increases. In the same manner, the Zener diode is also worked in same manner, just like a PN junction diode when it is connected in forward bias. Now, so go for the reverse characteristics of this Zener diode. So reverse characteristics, the graph is drawn between reverse voltage and reverse current. So when we are increasing the reverse voltage, there is a small changes will be occurring reverse current. That means approximately which maintains the constant current with the changes in. So in reverse bias, so reverse voltage increases, there is a small changes will be occurring reverse current. That means almost the current will be constant. So once it reaches the breakdown voltage. Once it reaches the breakdown voltage, there is a small changes in the reverse voltage. There is a sudden increasing in reverse current. So this reverse bias operation will be used as a regulator in case of Zener diode. So the working range of these currents, that means reverse current here is, so I minimum and I maximum. This region will be used for practical working voltage of a Zener diode. So that means here when we are increasing the voltage, here the practical working current or a practical working range of Zener diode is, so when the breakdown region will be occur. So after the breakdown region or breakdown point, so the small changes in reverse voltage, there is a large or sudden increment in reverse current. This region will be called as practical working range of a Zener diode. That is V maximum to the V minimum to the V maximum. This is equal to the minimum point and maximum point. In this region will be used as a practical working range of a Zener diode. So this Zener diode will be used as a regulator. In this case, we are going to discuss about the Zener diode shunt regulator. That means, so here the regulators having the two types in case of Zener diode. That is Zener series regulator and Zener shunt regulator. So in this video, we are discussed Zener diode. We are discussing about Zener diode shunt regulator. So the only difference between Zener series regulator and Zener shunt regulator is, so in case of Zener series regulator means the Zener diode will be connected in series to the load, then that will be called as Zener series regulator. Now we will go for the Zener shunt regulator. So the name itself, the Zener diode will be connected in shunt with the load. That means in shunt with the load means, so Zener diode will be connected in parallel to the load resistance. So the input coming from the regulator is either from rectifier or a filter circuit. From the rectifier circuit or a filter circuit mostly. So suppose you can assume as the filter output is so which smoothens the output of the rectifier. That means approximately DC voltage. So DC output as the output from the filter circuit is given as input to the regulator. So that will be applied as input to the circuit, that is Zener shunt regulator. Here the input current will be called as IS, that will be called as source current. So next the resistance will be called as RS, source resistance. The current flowing through this Zener diode will be noted as IZ. The current flowing through this load will be called as IL. So the total current of the source current IS will be equal to the sum of Zener current plus load current. The output will be taken across the load resistance RL. That will be called as regulated output voltage. This is about the circuit of Zener regulated power shunt regulator. Now, so the working of Zener shunt regulator is, so resistor RS, that is series resistor RS, is connected in series with the Zener diode to limit the current flowing through the diode with the voltage source Vs being connected across the combination. That means here the RS, series resistor RS, will be connected in series with the Zener diode. That means here this series resistor is connected in series with the Zener diode. So why we are connecting this series resistor with Zener diode means, so to limit the current flow through the diode with voltage source Vs being connected across the combination. That means when we are connecting the voltage source across the series resistor and Zener diode to limit the current flowing through the diode, so we have to connect the series resistor in series with Zener diode. So the stabilized output voltage Vout is taken from the Zener diode. So that means when source voltage Vs will be connected to this combination, that is Rs in series with Zener diode, which limits the current flowing through the Zener diode. Next, the Zener diode is connected with its cathode terminal connected to the positive rail of the DC supply. So it is reverse biased and will be operating in its breakdown condition. Here the cathode terminal of the Zener diode will be connected to the positive of the DC supply. So it will be connected in reverse bias and it will be operated in its breakdown condition. So the series resistor RS is selected so to limit the maximum current flowing in the circuit. So because of selecting the RS resistor, that is series resistor, which limits the current, the maximum current flowing in the circuit. So now, so with no load connected to the circuit, suppose, so for this shunt regulator, if there is no load will be connected to the circuit, so no load will be connected to the circuit means here there is no load resistor RL. So without load connected to this RL circuit, so how it will be work means, when no load connected to the circuit, the load current will be 0 because there is no load, so that's why the current flowing through the load will be equal to 0 and all the circuit current passes through the Zener diode and all the current passes through the Zener diode, which in turn dissipates its maximum power. All the circuit current will passes through the Zener diode because there is no load will be connected. So here Zener diode and load will be connected in parallel. So there is no load means the entire current of the circuit will be flowing through the Zener diode, which in turn dissipates its maximum power. The Zener diode will dissipate the maximum power. And also a small value of the series resistance Rs will result in a greater diode current when the load resistance RL is connected. So in first case there is no load connected. So now the second case is when the RL is connected in parallel to the Zener diode, a small value of the series resistor, the small value of the series resistor value will result in a greater diode current when the load resistance RL is connected, and large as this will increases the power dissipation requirement of the diode. So care must be taken when selecting the appropriate value of series resistance so that the Zener's maximum power rating is not exceeded under this no load or high impedance condition. Suppose, so when we are depends upon the selecting the value of RS value, so the power dissipation will be getting across the Zener diode by proper selection of series resistance will result in greater diode current when the load resistance RL is connected. So that's why we can select the proper value of series resistor so that which limits the current flowing through the circuit. So when the load is connected in parallel with the Zener diode. So in case of first case, there is no load will be connected. So load will not be connected to the circuit, mean the entire current will be flowing through the Zener diode. So by selecting the proper value of series resistance, we can avoid the any variations at the output end. That means it, so the power rating is not exceeded under the no load condition or a high impedance condition. So next condition here is the load is connected. Case 2 is when the load is connected in parallel with the Zener diode. So the voltage across R is always the same as the Zener voltage. The voltage across R is always the same as the Zener voltage, V equal to VR. There is a minimum Zener current for which the stabilization of the voltage is effective, and the Zener current must stay above this value operating under load within its breakdown region at all times. That means, so due to the minimum Zener current for which the stabilization of the voltage is effective, and the Zener current must stay above this region or above this value of operating under load within its breakdown region at all times. So the upper limit of current is of course depend upon the power rating of the device. The supply voltage V must be greater than VR. The supply voltage that will be equal to greater than the voltage drop across the series resistor. So when load is connected in parallel with the Zener diode, so then the voltage drop across R will be equal to or same as the Zener voltage. So by selecting this, when load is connected across the Zener diode, the minimum Zener current for which the stabilization of the voltage is effective, and the Zener current must stay above this value operating under load within its breakdown region at all times. By selecting the proper Zener value, resistance value, the Zener current will be minimum, then it will be operated in breakdown region at all times. So under this limit of this current, so the supply voltage V must be greater than the VR, that is Zener voltage. So the main limitations of this Zener regulator here is, so the limitations of Zener regulator. Here the first one is, it has low efficiency for heavy load currents. So the first drawback of this Zener regulator is, so when you are connecting heavy load to this circuit, the efficiency of the circuit will be low. It is because if the load current is large, there will be considerable power loss in the series limiting resistor. Suppose we are connecting the heavy load to this Zener shunt regulator, so the load current is large. That means the load current will be high. So this will be considerable power loss in the series limiting resistor. The power will be lost at the series resistor. Next, the second drawback in Zener regulator is the output voltage. The output voltage slightly changes due to Zener impedance. Slightly changes due to Zener impedance. That is as V naught equal to Vz plus Iz into R. Here Vz is equal to voltage drop across the Zener diode. Iz and Rz will be equal to the current flowing through the diode. So the output voltage slightly changed due to the Zener impedance. Next, third point is, changes in load current produces changes in Zener current. When the load current will be changed, the Zener current is also changed. Consequently, the output voltage is also changed. Because the load current will be changed, the current flowing through the Zener diode is also changed, because those two are connected in parallel. So that's why the changes in current will be occur due to changes in load current. So the changes in Zener current will make the output voltage is also changed. So these are the main limitations of Zener regulator. So this is the completely about the regulated power supply. That means totally in this chapter, so we have discussed about rectifiers, filters and regulated power supplies. So in case of rectifiers, so the AC supply will be, AC input signal will be converted into pulsating DC. In case of filters, the pulsating DC will be smoothened by the filter circuit. So to maintain the smoothened circuit or smoothen the output, we are using the regulated power supply. So in this regulated power supply mainly uses the Zener regulator. So To avoid the drawbacks in series shunt regulators, we are using the shunt Zener regulator. So, but here also some of the limitations. That means, so when we are using heavy load at the circuit, which will causes low efficiency. At the same time, while increasing the load current, which increases the Zener current, so that's why the output voltage will also be changed. Again, the output voltage will be slightly changed due to Zener impedance. That means the complete regulated power supply having the circuit elements are, so one is the rectifier circuit. So rectifier, the input for the rectifier circuit is AC. So next, the output of the rectifier is pulsating DC. This DC will be given as input to the filter circuit. So after the filter output, it will be given to the regulator. This is the final output. That means AC input, DC output, constant DC output. So how to get this constant DC output means rectifier circuit will provide the pulsating DC output. So the filter circuit will smoothens the pulsating DC signal. This pulsating DC signal smoothens output as input to the regulators, which maintains the constant output. Then we can finally get the DC output. That means AC will be given as input to the circuit. Finally, we can get the constant DC voltage. So this will be done by the three elements, that is rectifier, filters and regulators. So depends upon our applications, we are using the different types of rectifiers, filters and regulators. So overall discussion, we are using the rectifiers is full wave bridge rectifier. So in case of filter circuit, we are using the CRC filter or CLC filter. It will be called as 5-type filter. Next, in case of regulator, we are using Zener shunt regulators to converting the AC signal into complete DC signal. So this is the complete video lecture about the regulated power supply along with rectifiers and filters. So the Zener diode shunt regulator, the circuit diagram is very important. That is, so shunt means we are connecting diode in shunt with the load. Suppose diode will be connected in shunt with the load, it will be called as shunt. At the same time, Zener diode will be connected in series with the load, that will be called as series. So the total current, that is AC supply current, will be equal to source supply current will be equal to the sum of Zener current and load current. This is the Zener diode shunt regulator. Thank you.